Okay, let's begin. So, a lot of this is sort of redo of what we talked about on Friday. Um, Although it's probably a good idea to sort of write certain things down. Electric field is similar to a gravitational field. In some ways, there are similarities and differences. Gravitational field is defined as the amount of force exerted upon a unit of mass. Or on Earth, that is 9.8 newtons per kilogram. So that's sort of the definition of gravitational field. It's the amount of force exerted upon a unit of mass. And now how does that relate to electric fields? It's almost virtually word for word with sort of one or two little exceptions there. Gravitational field is defined as the amount of force exerted upon a unit of mass. You only have to change one word to be able to define an electric field. On the back there. No? Okay. So we'll get to that definition, formal definition in a minute. As well, gravitational field exists around objects with mass. Any object with mass, pencil sharpeners, garbage cans, globes, stuff, falcons, all have mass and all have gravitational field, right? So gravitational fields exist around any object with mass. Large masses, such as planets, like the ones we saw in the TED Talk, have a strong gravitational field. Things that are smaller, not so big. Okay, so I'm trying to show you sort of the similarities between gravitational fields and electric fields. Colin, you're going to walk in late. You still got to, Okay, awesome. Are we writing that test today, Colin? Writing that test today? Okay, so what about these electric fields then? So around any charged object, there exists an electric field. So objects with mass, gravitational field. Objects with charge have an electric field. And obviously, objects with a large charge have a strong electric field, and objects with a small charge have a small electric field. And these fields are shown by a series of arrows radiating inwards or outwards. And these are called lines of force, or field lines. And you've seen them already. There it is there. Okay, so around any charged object there exists this electric field, an object with a large charge. Yeah, I've been through that, right? Let's go back to this definition because I realized I looked ahead there and I really should have the actual definition. So what would you have to change to this sentence? A gravitational field is defined as the amount of force exerted upon a unit of mass. How would you change it so that instead of gravitational it said an electric field is defined as? I'll give you a hint. You only have to change one word. Where would I put charge in for? Yeah, exactly. Right? Like electric field is defined as the amount of force exerted upon a unit of charge. And what is that unit of charge? You would think it's 1.6 times 10 to the minus 19, but it's actually a coulomb of charge. And I don't know why it is coulomb. That's a good question. And I will have to tell you how many 1.6 times 10 to the minus 19s there are in a coulomb. 6.02 times 10 to the 23. Just have all these crazy numbers in my head that I wonder how smart I'd be if I could just get rid of all those stupid trivia things. And what? I saw a good one the other day. What the heck was it?
Oh, gosh.
Okay, we're good? Okay, so there are electric lines of force. Now, in this case here, They are pointing outwards. How come they're pointing outwards? Because it's positive, exactly. Positive charge, because what do we use to determine the direction? No, a small positive test charge, right? So it's the direction that a positive test charge would go, right? And as always, the closer the lines are, the stronger the field is, and this strength is dependent upon the distance, and this follows the inverse square law again. And what is that inverse square law again? No. 2 times as far away, 1/4 the strength. Inverse squared, 2 squared. 3 times as far, 1/9. 4 times as far? It's the number squared, Grayson. 4 squared. Yeah, I know. That's why I'm explaining it to you. Okay, what if it's 2.5 times as far? 1 over 2.5 squared. Whatever that is. No, you didn't see that one coming? Yeah, that's what the inverse square law says. 7 times as far? 1 over 7 squared. Or 1/49th.
So you keep the number on the left.
You take the number on the left, you put it underneath 1, and you square it. Inverse square. It's not hard. Okay. And again, to show the direction of the field, bring another smaller positive test charge nearby, and it will be repelled, right? We always use this positive test charge. I'm just kind of, basically I'm reviewing and telling you what we talked about on Friday, right? Reinforcing it. There it is there. This guy has a positive charge, right? Now, if this was a negative charge, if this is a negative charge, then that small positive test charge would be attractive, wouldn't it? Right? Always test it with a positive test charge. Now, here's a question for you. This is basically a year in review question. What would be the acceleration of this? Would it remain constant? Like right here, if I'm just going to redraw, I don't know if I can move it, but right there, is that the same? Is it going to have the same acceleration as it would there?
No.
Yes.
Further.
It's further away from the original, that's true.
It's really weaker.
Which would mean that the field would be weaker.
Only very little.
So that would mean that the force on it would be less. And does it have the same mass? So what would the acceleration be? More, less, or the same? The acceleration would be less. The acceleration would be, assuming no, even if there was friction, the friction here and the air resistance here and the air resistance there would be the same, right? So the acceleration here would be less. Now, if the acceleration here is more, it means it's speeding up. Does it still mean that it's speeding up here? Yes, just not as fast. Just not as fast. Right? So it'd be going really fast at the start, right? Sorry. It would be accelerating really fast at the start, and then its acceleration would be less and less as it went out, but it would be traveling faster and faster. It would have a jerk factor. Jerk. What a jerk.
What is it when
The jerk factor is the rate at which the acceleration changes. Algebra with a positive charge, that field's a point away. If you were to have a large negatively charged object, the positive charge is attracted, right? We've been through all this. We don't even need to write this down, do we? I don't even know why I got this. Here it is. This amount of attraction or repulsion can be used to indicate how strong an electric field is. The field strength is defined as the force the field exerts on a unit of charge. The field strength is defined as the force the field exerts on a unit of charge. And that unit, again, is the Coulomb. Charles Coulomb, French scientist, I believe. The force the field exerts on a unit of charge. Hey, let's do some formulas. You know, we don't have enough formulas. Let's give you another one. Done any exam preparation?
Clean it up.
Yeah, just. And there it is. There's the formula. E equals F over Q. The electric field E is the force per unit of charge Q. Okay? So E is the field intensity or strength measured in newtons per coulomb, which I know is in the video project. Right? So newtons per coulomb is what you measure an electric field in. Fe is the force. Why is the E there? Because it's the type of force. So in this case, it's the electric force, right? So the E is just a subscript for labeling what kind of force it is, measured in newtons. And Q is the charge in coulombs or C.
I remember doing this in grade 1.
Yeah?
Yes.
Yeah, I think we did do Q in grade 9, yeah. Some charge. We did static stuff, yeah. Pardon me? F, well, C is the unit, right? Q is the letter. It's like F is for force, and it's measured in N newtons, right? D is distance measured in M meters. So C is the unit. Q is the letter. Now, this always comes up. The intensity or strength of an electric field is the same for a positive charge as it is for a negative charge. Only the direction is different. So if I have an object with a charge of plus 5 coulombs, same field strength as if it were minus 5 coulombs. My goodness, that is an excellent true or false question.
It's the same.
Yes. Right? The strength of the electric field is the same for a positive charge as it is for the same negative charge, right? Like if it's both plus 5 or minus 5, the force is the same. Only the direction differs. Do these seem like simple problems to solve? E equals F over Q? No? Because it's just going to be like a divide by, isn't it? Eventually, yeah. But just these ones are pretty easy. Don't worry, I figured out a way to make them hard.
Thanks.
You're welcome. Oh, that's my job, making things hard. Good? Good, good, good? Okay, here's an example. I apologize. I'm going to make you write it out. But it's pretty simple. Just going to do my attempts. The hardest part of these questions is dealing with scientific notation, which I think we've already looked at a little bit. Am I not right? Did we talk about scientific notation yet? We have, right? Kind of, not really? Okay, so then we'll have to deal with that. 2.4 times 10 to the minus 6 coulomb experiences a 3.2 Newton force. So we're looking for the electric field intensity. We are looking for the value of E. What is the electric field intensity, electric field strength? We're looking for E. What's the new formula? E equals F over Q. Okay? So the force, a 3.2 Newton force, the force is 3.2 and the charge is 2.4 times 10 to the minus 6. All right, so how do we do this on your calculator? You should have somewhere on your calculator one of the two buttons. Either EXP or EE. EE. Sometimes it's second function, which is unfortunate for some people. The EXP generally is not. It's usually its own button, right? And it means times 10 to the power of. That's what it means. You do not need to go times 10. EXP does it for you. Okay? So with your calculator, you're going to go 3.2, and you should do this with me.
Divided by.
3.2 divided by 2.4, and then to get the times 10, EXP or EE, whichever one you have, and it'll put a little symbol in there, right? And then you go -6, and you should get 1333333.333.
Yep. Oh, let's do this one.
Yeah, I would prefer it scientific. So the general rule is that once you get sort of like 4 decimal places, you should probably go to scientific notation. Now, if your calculator doesn't do it automatically, you can put your calculator in scientific mode, okay? And everyone's calculator is different, and I literally have to walk around and show you how to do everyone in there. So I will do that in a bit, right? But usually you can find it. If you have an FSE button, you're in luck because that's the easiest way to do it. And I don't see too many of those calculators much anymore, but usually it's under mode or setup or something like that. I usually have to go digging to find it. But you can turn your calculator in scientific mode, and it will put your result in automatic scientific mode. The calculator doesn't do that unless it's like 8 or 9 digits. Then you got to be able to count.
That was really cool numbers.
Yeah. So I'll come around and I'll show people how to do that once I give you the handout. Let's try one more question here.
How come this time changed on the 6?
Oh, it did. Oh, well, no, because when you take that and divide by it is, right? And when you do, this is a really, really, really small number. When you divide by a small number, you get a really, really big number, right? Yeah.
It shows that on your calculator?
Yep.
Okay, I don't know.
Yep. Okay, so try example number 2, if you want. It'd be a good chance for you to try, actually. So yeah, you guys try that, and then I'll give you the answer in 3 or 4 minutes. An object of charge, that is the Q, is in a electric field of 2 times 10 to the 4 newtons per coulomb. That is our E, and you're solving for what? Force is applied. So E equals F over Q. When you solve this, how do you solve it? You're multiplying. So you're going to go on your calculator. You're going to go, here's the steps. You're going to go 2 EXP or EE, whichever one you have, 2 EXP4 times 1.0 EXP minus 6, and you make sure you have to hit equals. And you might actually get, if your calculator's in scientific mode, you might get 2.0 times 10 to the minus 2. Either of those is fine. Okay? So what I normally do now is I hand up the problems, and then I sort of wander around and help people with the calculator.
Normally do, but let go.
So that's what I'm going to do.
A lot of mistakes.
Yeah, well.
Hey.